Good afternoon, folks. We're here to talk to you about scaling for success. I'm here with my esteemed colleagues, Jason and Wieste. I'm Belinda Runkle. I run serverless engineering. So roughly 10 years ago, almost to the day, back in October 1st, 2013, was one of the most infamous site launches and traffic surges in history. No, it's not Taylor Swift tickets. Healthcare.gov. Many of you have probably heard this before. It was the healthcare signups as part of the Affordable Care Act under the Obama administration. And it was a way that individuals could get healthcare where they had never been able to have access to healthcare before. As folks that already know the story know, it was a massive failure. They had 250,000 users that crashed the site in the first 2 hours. Despite having 250,000 users, do you know how many people actually made it all the way through the site and got healthcare on the first day? 10,000, maybe 100,000. Six people got healthcare that day. The repair took months. Their initial budget was about $94 million. Pretty healthy budget for a website, I would have thought. But actually repairing it cost $1.7 billion. To the American taxpayers, we are now very aware of this. Actually, if you adjust for inflation, that's $2.2 billion. It's a lot of money for a traffic surge. So we're going to talk to you today about traffic surges and how to prepare for them. Now, why is this hard? You know, in a scalable system, what we need is a system that performs with high reliability, low latency, independent of load, which will fluctuate, all while managing for cost. Now, when we talk about scaling for today, we're going to talk about Cloud Run. Cloud Run is very good at auto-scaling, as we're going to tell you more about. And what is Cloud Run? So Cloud Run is a fully managed, serverless container runtime environment. You can build sites, jobs, services, pick any language, deploy in seconds. And underneath the hood of Cloud Run is an auto-scaling system, which automatically scales to the number of instances needed to handle the incoming traffic. It even scales down. So when traffic goes down, maybe at night, you can go all the way down to 0 instances. So in a traditional capacity management situation, maybe you're managing for VMs or for hardware, a place where you don't have an autoscaler, you got to provision for peak utilization. Even if that peak is short or kind of lumpy and inconsistent, and as we all know, that can be very expensive, especially if you end up provisioning for a lot more than you need, which is clearly not a problem that healthcare.gov had at the moment. But under provisioning is worse, right? Because you end up with latency, errors, potentially some lost traffic, lost conversions, or lost revenue, all the bad things. So, easy, just over provision. Provision for peak, provision for what you expect, and aim perfectly, problem solved. It is actually a legitimate approach. There's a lot of people still doing it, so don't knock it. But throwing money at the problem is super expensive. And how good are you at predicting the future anyway? So predicting when and where load will happen is actually a very complex, in a complex system, is a very difficult problem. Do you know which services are CPU bound, which are IO bound? What happens when the traffic slows down? What happens when it falls over? How lumpy it is may depend on things like your load balancers and your caches and how other parts of the system perform. And does it even ramp down when you don't need it so you don't overpay? How well does your load testing actually simulate real user traffic when there's a load? And then there's agility. Agility is about how well does the system respond to those changes in traffic? So when the utilization needs, drives to scale up or scale down, how well does that system respond? Now that is partially dependent on how good your autoscaler is, and we will tell you later about how great Cloud Run is with their autoscaler. But that's only part of the story. The other part of it is how quickly your application loads on a container and can be ready for requests. And this is when we talk about cold starts. You've probably heard the word cold starts before. Cold start is the time that it takes to load the application on the container and be ready to respond to request. Until that very first request goes through, there's a tax that you pay, which is the cold start. Now, we say cold start, it's almost like a little bit of a dirty word in the industry, but cold starts are very normal. So from 0 requests to that one first request, that first instance of that first revision is always going to have a cold start. You can't avoid it. As soon as you need to scale up to a second instance, you're going to pay that cold start tax again. Now, you may get second, third, fourth, 500,000 requests through that first instance. You're not going to keep paying that tax. Those are warmed instances. And again, what I'm trying to emphasize is that this is normal. There are some optimization tricks, even if you don't have an autoscaler. You can do things like give it more CPU, give it more RAM, all these things that will boost that startup time for your container and your application. You can look at pre-warming instances, right? Kind of a little trick, so that you basically pay the cold start tax ahead of time before the traffic surge. But ultimately, you need that scaling logic to be nimble enough to respond to traffic with the right number of instances appropriately and quickly enough, and not get bogged down by the cold start tax from your own application. And last, much like healthcare.gov learned, you can't just scale up one portion of the system without it potentially affecting other parts of the system. Let's say I have a web service and it does some synchronous write to a database. Now I scale up 1,000 instances of that. My database is going to be struggling. It sounds really dumb, but you see it all the time. It happens all the time in production systems. Lots of opportunities to mitigate that, of course, right? You can do a service in between. You can shard the database. You can not use the database. Instead, write to a queue or write to an event pipeline and eventually write to the database. So there's lots of ways to get around it. We'll talk more about patterns for isolation a little bit later. So how does Google do this? So Google has been scaling for a very long time on a very diverse set of systems. Think about all the different products that Google makes. And we make it incredibly easier for our developers to build and scale systems, right? We don't require that our developers have to all be scalability experts. Instead, we build a very scalable system that makes it easy for them to be able to scale. And the way that we do that is through one of our most well-known systems at Google, which is Borg. Now, what is Borg? Borg is Google's internal cluster manager. It's the way that we run containers at scale inside of Google. And Borg was actually the original system that Kubernetes was designed after. And Borg itself was really tailor-made for Google's scalability challenges. Now, you might be surprised to know that Cloud Run is actually a product descendant of App Engine. Folks may remember App Engine. It's still a very popular product, both inside and outside of Google. And with App Engine, we could help developers write their own code in whatever language, whatever frameworks, all the tools that they want, package it in a container, host it, scale it, only bill for the resources that you need. In practice at Google, App Engine was the first way that we enabled getting user code to run on shared Borg. And so Cloud Run actually inherits some of the best parts of App Engine, as well as the best parts of Borg. Everything from containers to scalability, all in support of pay-as-you-go. And then the way that we build systems at Google really supports the ability to scale, and there's kind of 3 major sort of principal areas that we'll talk about. Oops. Okay. The first is multi-tenancy. So with a huge diversity of workloads, many different resource types required, different capabilities, file systems, et cetera, and then we have a very diverse set of machine types, resources. Think about the many, many years that Google has been in production, racking and stacking across our data centers. The Borg is able to tailor resources to meet the requirements of those workloads with strong isolation on every instance so we can avoid noisy neighbor effects. We bin pack the containers for maximum efficiency while also providing prioritization of workloads, which developers can help control, but there's also an overarching prioritization mechanism. And then we auto-scale and resize beautifully as resource needs flex based on the needs of the fleet. The second is we require stateless services. For those of you who've heard the phrase, cattle not pets, all Google workloads need to be cattle not pets. There are some exceptions, but mostly they need to be stateless. And what that means is if one dies, it's hurt, we don't have to take it to the side and diagnose it. We assume it is going to be replaced. And that means that that job, that workload, cannot require interim state information. Everything must be restartable and repeatable. And this allows us to get back to a healthy state very quickly and automatically. Developers' intervention is not required. And so in Google, Failures are a very normal occurrence. They are not considered interruption. And then third is experimentation. So we advocate very strong production principles that allow us to manage the risk of disruptive changes at Google. We support experiments with progressive rollouts. It includes the ability to roll back. And we implement inside of our experiment system metrics for measuring for correctness, for making sure that it has the right outcome in production. We can then gradually ramp up changes by a percentage, for targeting certain regions. We can add criteria. We can verify the change, detect problems early. And what it means is when we roll out a bug, and we do roll out bugs, they happen all the time. But with this mechanism, we limit the impact. So when a bug goes into prod, it only affects a small portion of customers before it's caught and rolled back. So we make it safer for our developers. All of these core ideas have made their way into Cloud Run as a product. But I'm going to stop talking to you about it. It might be easier just to show you. So my esteemed colleague Wieste would love to give you a demo and talk to you more about scaling with Cloud Run. Go ahead, Wieste.
Thank you. OK, so I'm here to send many requests to a Cloud Run service. But let me explain what this example service does first. It is, it gets a request. It will wait for 1 second. And then it will compute a few prime numbers to burn some CPU cycles. And I hear you thinking, is this a good example? Like, raise your hand if you're computing prime numbers in production. I was afraid this would happen. No, but really, your service might look like this instead, right? You get a request, and then you need to send a request or a query to a database to get some data, and that's when the waiting starts. And when you get the response back, it will, you'll need to process it. Maybe put it into an HTML template and render it back to the user, or call another system and, well, burn some CPU. And that's the same thing as I'm doing in my example service. But Wieste, I hear you think. The whole system needs to scale. I mean, it's good that you can scale all those containers, but what about the database? I mean, Belinda referred to that. It's not about the containers in isolation. I don't care if you scale 1,000 containers. The whole system needs to scale. I know, but this demo is just about Cloud Run, and Jason is going to teach us some patterns how to deal with scaling the entire system and serving all the requests reliably. Now, how do I generate load for my example service? I use an infinite loop, so while true, send request. And in fact, I use many of those infinite loops. And I've also built a little visualization, right? Because, yeah, well, it has to be live, because otherwise it won't be believable. So the visualization represents a load-generating client as a red circle. And this is not a user, it's like the infinite loop, because most users don't like refresh all the time, unless, well, maybe if the system is too slow. And this is what it does, right? All those infinite loops send requests to my Cloud Run service, and Cloud Run starts container instances, and I represent those as green squares. And I show the green square as soon as a container instance is ready to serve a request, right? So container instance lifecycle, Cloud Run decides to start a container instance, it starts, and as soon as it's ready to serve requests, I paint the box on the screen. So that might mean that you see a bit of lag in the visualization, right? So a bunch of requests coming in, and Cloud Run decides, ooh, this is a lot. I need to start container instances. It will take the container instance startup time before you see the request. Now let's get started. And this is the live part of the demo. Live demos are also always a bit scary. I practiced this morning, and this was what I saw in Cloud Monitoring. But yeah, well, let's go. I have 4 modes, like no traffic, well, that's where we're at now, regular traffic, a traffic search, and Jason told me not to press the last button, but I will do it anyway. And there's the number of requests, which will count up, hopefully, and very important, the success percentage. Like maybe if we're scaling out, the request might be a bit slower, but it matters if we serve them or not. So hopefully, this will stay 100. Okay, are we ready? I don't feel ready, but I'm going to press regular traffic. And we'll see 10 infinite loops appear, and Cloud Run is going to start, yeah, 3 container instances. And every container instance is 1 CPU and 512 megabytes of RAM. 120 requests served, all successful. So now, I'll press search traffic, and we'll go from 10 clients to 2,000 clients, infinite loops, in, well, milliseconds. There you go. And Cloud Run starts to scale. It will take a while. Yes, there we go. Okay, apparently 60 instances is enough to handle the load. Well, it decides that it needs more. Right, and we're not dropping requests. That's kind of the important part, because, well, of course, if there's a sudden traffic increase, your latency might increase. Like if you want to prevent that, you need to have a lot of instances warm already, right? That's why we have idle minimum instances. Yeah. Do you want me to press the last button? I was afraid you would. Okay, for 6,000, 8,000, 10,000. I wonder where I set the limit. Well, this is going to exercise Cloud Run. And the number of requests served is, I think I'm going to stop when it's at 1 million. Ooh, it's now really deciding to start more. Like by default, you can get up to 1,000 container instances in a Cloud Run service. But that's the maximum that we can lift for you if you need even more. But like, keep in mind, this is already, well, 800 cores. So that's likely enough for most workloads. It worked. I'm happy. Was this a good show? Cool. Well, I'll turn off the traffic now, and we'll likely see Cloud Run react quickly and reduce the number of container instances, because it will scale down. And there's a couple of things you need to know when Cloud Run starts scaling down. By default, the pricing model in Cloud Run is such that you don't pay for the container instances while if they don't handle requests, right? So there's no request coming in. I'm not paying for those 958 container instances. And we guarantee that in 15 minutes they will be stopped, but likely a few are disappearing already. So like on the chart I showed earlier, you could see that it would like gently taper off. That was my demo, and I'd like to invite my coworker Jason on stage, who's going to teach us all about like the more difficult parts of, I mean, getting container instances go bzz is easy, but the hard part is in actually designing the system. So, Jason, come on up.
Thank you, Wieste. Yes. I assume the applause was Wieste, not just me coming on stage, but I'll take it. Okay, we are back to the slides. Hi, everybody. I'm Jason. That was the demo. So Wieste just showed you a demo of synthetic load to Cloud Run and how it's able to scale up. And Belinda talked about how we solve for some of these scaling challenges at Google. And so with Cloud Run, what we've tried to do is bring some of those capabilities through the product in Cloud Run without you having to do any of it yourself. So natively, Cloud Run is multi-tenant. It runs on shared Borg. Why should you care about that? Actually, you shouldn't. But what it does allow us to do is give you that behavior that Wieste talked about, where you only pay while the request is in flight. Now, we can do that because of the multi-tenant nature of the infrastructure, and we're able to bin pack these workloads efficiently, and that allows us to provide that capability to you. It automatically scales. As we saw, we use two main signals. One is the number of concurrent requests that we're receiving on an instance, and the other is the CPU utilization of an instance. What Wieste demonstrated was one core per container. So I think we got up to 900 and something cores in, a few seconds, which is pretty impressive. You can also do that across regions. So you can have as many Cloud Run services in as many regions as you want and scale them sort of as a unit. And again, that's really advantageous with the scale to zero and pay for what you use model, because if a region's not getting any traffic, it's costing you $0. So you can sort of have as many regions as you like for very low incremental cost. And lastly, in the box comes traffic splitting, which is our sort of version of the experimentation that Belinda talked about, where rolling out a version of your application is not just rolling out a version of the source code, it's also rolling out the configuration that you've chosen as it relates to scaling. So Belinda talked a lot about some of the challenges and some of the pitfalls with scaling. What I wanted to do is take you through some actionable tactics, some techniques that you can use to help your application prepare for these unexpected surges in traffic. And there's really 4 things that sort of operate in a loop here. The first is just to understand where you are today, measuring what your cold start time is, for example, what your goals are, what are you trying to achieve from a latency standpoint, and that will help inform these other 3 steps. The second one is workload optimization. This is your application. What can you do to reduce the cold start time, to reduce the execution time, if your application would benefit from more concurrent requests on an instance? Does that have implications to your application? Are you going to run into race conditions and deadlocks and things like that? The third box there is system design. That's more about the architecture of your application. Is it designed as a model to scale well, or is it just going to be hard to scale no matter how good the infrastructure underneath it is? And lastly is the system configuration. That's how have you configured the system itself, in this case Cloud Run. What knobs and levers have you exercised there to best fit your applications? So we're going to go through all 3 of these steps. Okay, workload optimization. Belinda talked about cold start and cold start, cold start, cold start. We keep hearing about it. I wanted to just do one layer of the onion peeled away, just to a little bit more of an explanation as to what this means. So the green is the request coming in, and the yellow is the response going out. In Cloud Run, the request hits a front end that we control, part of our data plane, and there's a little bit of time spent there to route that request to an available instance, or in the case of no available instances, to instruct the system to create a new one. Most of the time is going to be spent in your container processing that request, and then the response comes back, and the difference between the 2 is what we typically refer to as latency. In a cold start scenario, the request comes into our infrastructure. In the case where there wasn't an instance, or we felt that there weren't enough instances, we need to create a new one, there's that penalty, that tax that Belinda talked about that we refer to as cold start, which is just additive. It just adds to the latency, because we have to sort of wait for that instance to become viable, then send the request to it, and then it has to process that request. Now, if you look at this, and we've said a lot about how good our scaling system is, you might think to yourself, actually I had one other point here, and that is that if that end-to-end latency, maybe your client has some sort of timeout configured, so at the extreme limit, you might start getting errors because your clients are timing out. You might look at this and say, well, okay, but why didn't you all just create the container before you needed it and consume that cold start penalty when it wasn't needed? And in fact, we do. We do exactly that, but I wanted to just do a little bit of a further deep dive into why that sometimes is not enough. So this is a chart. Imagine that, so on the x-axis is time, on the y-axis is load. Load could be number of requests, QPS, whatever you like. And so you can see in this chart, it's sort of growing slowly, steadily, and then we see this uptick, this sort of rapid surge in traffic. The light blue boxes here are representing the number of instances. We saw I should have chosen green squares because it was in Wieste's demo, but nevertheless. And so when the traffic is gradually rising, there's a point at which we have a signal that says, we probably might need a new instance soon. This is when I referred to sort of spinning it up ahead of time. So that's the red line there. Let's say it's CPU utilization. And the CPU gets to a certain point where we say, you know what, we think we're going to need a new instance soon. So we start spinning up an instance, and it takes a certain amount of time to start. But actually, we don't need it immediately. Those two green lines are representing the time at which we get the signal, okay, you need a new instance, and the time at which we need the instance, because the traffic hasn't gotten yet to the point that we need it. So we've got that amount of time to react. We've got that amount of time to create an instance and get it ready before the traffic, before we actually need it. So that works fine. Then later on, when this spike happens, we have the same scenario. We get a signal, that's the red line, and we need that new instance when the traffic reaches that point. But in this case, that time is much less. And so what this is saying is that the steepness of the curve in traffic determines how much time we have to react. Now, if your cold start time is longer than the time that our system has available to react to the change in traffic, then you can run into this situation where you're not going to have an instance ready when the traffic hits. So as good as, you know, outside of changing physics, which we're also working on, there is just a fundamental limit that's just the nature of how the universe works. Having said that, Cloud Run does have a fancy feature that we call rapid scaling. And you may not have noticed it, but you would have seen it in the demo that we just saw, where rapid increase in traffic and then a sort of slow increase in instances and then a sudden increase in instances. And what the system is doing is saying, okay, you got new traffic. Whoa, you really got new traffic. And so we will more aggressively allocate instances to accommodate for these very steep curves in traffic. Okay, so that's all about optimization. The shorter you can get that cold start time, the steeper the curve you can handle. The next thing I want to talk about is design. Belinda and Wieste both mentioned some patterns. There are many patterns that you could implement. I just chose two for today. Async deferral, and I don't know if these are really the names that they're supposed to be called. That's just what I called them. Also known as the not everything has to be synchronous, you know, pattern. So let's say we have some application, an e-commerce application, and there's a endpoint or a step or a function that is ordering items. So the customer's ordering an item. There's all sorts of problems with this number of steps, by the way, race conditions, whatever. Let's pretend they don't exist and this is real. So we're going to check the inventory to see that the item's available. We're going to check the payment instrument, that their credit card on file, as far as we can tell, is valid. Then we're going to create the order. We're going to charge the customer the money. We're going to update the inventory to say, okay, we've got one less item now because they just bought one. And then we're going to send them a confirmation email. And that's sort of the step of ordering an item. And then we look through the execution of that, and the check inventory and check instrument are pretty quickly. They're just doing a read operation on some data source. The create order is a little bit slower because we have to do an insert, and that's a little bit slower. Charging customer, maybe we're using some external payment gateway, and that is a bit slow. Updating inventory, maybe there's some sort of mutex we have to lock on to check that the inventory is still available, and etc. And then for some reason we have a very slow email server, and that takes forever. And so what can we do to make this faster? Well, if we look at it, we might say, well, not everything has to be synchronous here. There are some things that we can defer to a later time. And so we might look at the slowest of these steps and say, actually, we're going to move those somewhere else. We're going to simplify the synchronous part of the transaction to just be these 3 steps, and then we're going to enqueue a task onto some asynchronous queue, ideally a queue that has this semantic we refer to as at least once, so that we're guaranteed that it's going to succeed. And then you can execute those last 3 steps on another Cloud Run service, or you can use some sort of workflow if you want to have a sophisticated orchestration of those steps. This has a couple of advantages. One, the execution time is much smaller, and so you can, back to that chart before, you can scale more quickly. And the second advantage is that you can potentially get better reliability because you're moving some things off that critical path. Maybe your mail server is unreliable. With an at least once queue, you can have retry semantics and so on that will move that less reliable component off the critical path. So this is one thing that you can do from a system architecture standpoint. The other thing is this impedance mismatch that Belinda referred to, or this idea that the scalability of the front end is so good that it DDoSed your own database. And we've actually seen this happen inside Google, where so many front end services spun up and opened so many connections to a back end that the back end just melted. And that can have cascading failures for other systems that depend on that back end. And so what we generally do in these cases at Google is create an intermediary proxy or intermediary service. So in the case of a traditional, let's say, SQL database that has a fixed number of connections available, you create a service that is the only one authorized to access the database. And you manage those connections quite tightly, and then other services feed into that intermediate proxy service. In Cloud Run, you can do this. So the green boxes could be another Cloud Run service, and you can impose a maximum on the number of instances. So if your database has a fundamental limit, or if it's an external API and you have quota, you can impose a maximum there. And if you want to get really clever, you can, in that intermediate service, start thinking about things like implementing a priority system. So really important services come first, and less important services get a lower priority, and that would be mediated by this intermediate, what I've called here a fan-in proxy. Okay, lastly is the system configuration. So this is how, in the context of Cloud Run, how do we recommend you set it? There's only really 4 things that you need to think about in Cloud Run. One is, and we've alluded to both of these, I think, minimum and maximum instances. So minimum instances is, rather than scaling to 0, scale to some integer, 1, 2, 3, whatever it may be. The 0 to 1 scaling is sort of never going to go away as a challenge. If you want to scale to 0, you're always forever going to have a cold start on 0 to 1, unless you specify minimum instances of 1. What that does is it keeps an instance around, but because if that instance is idle, like it's around and it's alive but it's not being used, then the CPU is mostly idle. And so it's actually charged in Cloud Run at about a 90% discount. So you can have those instances sitting there waiting for traffic. When traffic hits, you've already paid the cold start for that instance. And so that 0 to 1 scaling event sort of goes away. And maximum, which I just referred to before, is imposing an upper bound. So this is sort of lower bound, upper bound of scaling. Concurrency, I don't know how readable that chart is, but concurrency in Cloud Run refers to how many requests are served simultaneously on a single instance. This is probably relevant or maybe familiar to those of you who have used a functions as a service product like Cloud Functions or like Amazon Lambda, where it's a single concurrency model. What that means is that a request comes in and it's allocated to an instance, the instance serves that request. If another request comes in at the same time or very close to it, it will allocate a new instance and it will go to the second instance. That's a concurrency of 1. And you can see the great efficiency gains that you get by having greater concurrency. The more concurrency you have, the fewer instances you need to serve the same amount of traffic, the fewer cold starts you'll incur, the better you can scale. So it all sort of leads to the same conclusion. So that order item example that I gave before, I was talking about execution time, I wasn't talking about cold start, but shorter execution time means more concurrency on that instance, typically. So you can see here in the example that for approximately the same amount of load, with concurrency of 1, the system needed 550 instances to serve that traffic. With a concurrency of 80, we only needed 150 instances. So that would have been 550 cold starts versus 150 cold starts. The third thing is instance sizing. Very often, not always, but very often cold start is CPU bound. It's a lot of loading of data and loading of libraries, and there's I/O happening, but it's a lot of CPU action, and so more CPU can reduce the cold start time. And then lastly is region selection. In GCP, not all regions are the same size. And so if you have a very high scale requirement and you need way more than 1,000 instances, maybe you need 10,000, then you want to be sure that you're choosing the right region. If you look in Cloud Console on the quotas page, it'll tell you what the absolute maximum is on a per region basis. And when I said there's only 4 things that you need to remember, I lied. There are 5. And the last one is coming soon, that's why it's a 5th one. It's a new feature we're introducing called service level minimum instances. I'm not in charge of branding. But what it really means is that you can set, previously for anyone who's used Cloud Run will know, that minimum instances feature is on a revision level or a version level. And in order to change it, you needed to redeploy your application, which is fine, but kind of annoying. What this allows you to do is essentially change that value without redeploying the application. So the use case here is things like if you know that there's going to be an event, maybe you're launching a product or you're doing some big announcement and you know there's going to be a spike in traffic, you can schedule an increase in this minimum instances using a cron like Cloud Scheduler or something like that. And so you can preemptively spool up a bunch of instances and make them warm in anticipation of a surge in traffic. The last slide. So just to summarize, step number 1 is to measure what you're doing, where you're trying to go, what your goals are. Spend some time optimizing your cold start time, your execution time. Look at there's ways to move things off the critical path. If you can, make them asynchronous. Think about the design of your system. Sometimes these settings take a while to dial in. What's the right CPU setting? What's the right concurrency? These are all very workload specific. It's very hard for us to know exactly ahead of time how much CPU would be optimal for your application. And so using those gradual rollout, the traffic splitting mechanism to iteratively find the sweet spot in your scaling setup.